Howdy, IB Math. It is Ms. Kosh. I came up with a new way to teach independent, the formal definition of an independent probability today. So hopefully I can make it through and show you on YouTube what I did for those of you who may have been absent or whatever. Okay, we talked last time about how this is A, this would be not A, this is B, this is not B, this is B, this is not B. And so when we're labeling the different parts of this tree diagram, we would first start with, okay, so what's the probability of A? And then, well, then we would look at the probability of not A over here, keeping in mind that these two branches should add up to 1, because either it's A or it's not A. And then, okay, so once event A has happened, we may see, okay, what B either can happen or it won't happen. And so this branch is the probability of B given that A has already happened. Okay, this one would be the probability of B not given that A has already happened, etc. I'm just going to do part of it because I just want to trace this branch. So this piece right here, we would write out this is the probability of A intersect B. Okay, so how did we find that? Well, we said it was the probability of A times the probability of B given A. Okay, and we talked about that a little bit last time, so hopefully this is somewhat familiar to you. Because, so like the idea was, we did a problem before. We have a bag A and a bag B, and bag A has this many red marbles and this many blue marbles, and bag B has this and this, whatever. Okay, so then what's the probability of getting a red marble versus a blue marble? So we would say this was the probability of bag A versus, not bag A, so bag B or whatever. And then the probability of red versus a blue, red versus blue. Okay, something like that. And so we would find this event right here by multiplying this by this, and it give us this one. Oh, that was confusing. Hopefully that made sense. Okay, so when we start talking about the formal definition of independent, what that means is two events, A and B, are independent if the probability of B given A is also just equal to the probability of B in general. Okay, so what happens with A is doesn't impact, sometimes I get my terminology a little bit off. So if you are a statistician and you know that I'm saying this wrong, correct me and help me out. But basically, events A and B are independent if the one of them has no impact on the other, okay? And so the probability of B given A would be equal to just the probability of B. Well, that means we can come back to this equation up here. Well, so this is true. This is not always true. This is true if A and B are independent. Okay, when they're independent, we can say that this must be true. Or if this is true, then we can imply that these things are independent. Okay, so now let's take this. We said that the probability of B given A is equal to the probability of B. So I can plug that in up here. You can't see what I'm doing. I can plug that in up here, and I find that the probability of A intersect B is equal to the probability of A times the probability of B. Okay, now this is only if the events are independent. So we could say the probability of A intersect B is equal to the probability of A times the probability of B if and only if. Okay, so it has to go both directions. If this is true, then A and B are independent. I'm too lazy to write out the whole word, okay? If they are independent, then we know that this must be true. Keep in mind, we talked before about this formula. The probability of A union B is equal to the probability of A plus the probability of B minus the probability of their intersection. Okay, this is always true, always and forever. It doesn't really matter what's happening with A and B. This would always be true. Okay, because we were just multiplying things along in this tree diagram. This one right here, well, these two are true if and only if we have independent events. Okay, so you have to be careful. We can't just use this because we feel like it. We can only use it because we already know that A and B are independent. Okay, so now they're going to give us a scenario. I'm going to give you a scenario. And I give you some information, and you tell me, are they independent or not? And so what I would do would be, well, we know the probability of A union B is always equal to the probability of A plus the probability of B minus the probability of A intersect B. Okay, so this is 0.8, this is 0.5, this is 0.6, and what do I have to subtract away? I see 0.5 plus 0.6 is 1.1. If I subtract that away, I get a negative 0.3, so probability of A intersect B is equal to 0.3. Okay, if they're independent, then the probability of A times the probability of B will be equal to that. Well, the probability of A is equal to 0.5 times the probability of B is equal to 0.6. 0.5 times 0.6 is 0.3, which is equal right here. So are they independent? Yes. A and B are independent. Okay, I had a couple more problems. This one I took a while to do in class, and to be honest with you, I'm not sure that I have to, because here's how we would interpret this. If they're independent, then the probability of A and the probability of B given A should be the same as the probability of just B, which should also be the same as the probability of B given not A. And these two are not the same, so I think they're not going to be the same. But we can manipulate equations, and let's play with this for a little bit. What we know is that the probability of A, what was I going to say? Okay, so from a second ago, we have this equation. The probability of A times the probability of B given A will be equal to the probability of their intersection. Okay, we could think Venn diagram too. Let's see. If this is A and this is B, so A is, I just put A on the right and B on the left. The probability of A intersect B, no, what we want to do is the probability of B given A would be this little piece over the whole thing. So it would be the probability of the intersection divided by the probability A, which gives me this equation. It's another way to look at that. Okay, I didn't really need to do that. So let's see. We know the probability of A is 2/5. We know the probability of B given A is 1/3. So therefore the probability of A, well, this would be 2/15. Okay, let's change that to 2/15 is equal to the probability of A intersect B. Okay, and in our Venn diagram, that region right here would be that intersection, and that's 2/15. So then the probability of A, this whole thing, is 2/5, which is equal to 6/15, right? Multiply 3 over 3, which means this whole circle A is going to be 6/15, so this would be 4/15. Okay, let's see. So what did we use? We used, okay, so now let's look at the probability of, over here, this would be B intersect A naught. Yes? And so the probability of B given A naught, do I want to do that next? Is this divided by the whole thing? I don't know that that's helpful. Hang on. I did this differently in class today. Okay. The probability of B given A naught will be equal to the probability of B intersecting A naught divided by the probability of A, oh, I did know how to do it. Okay, I'm sorry. The probability of A naught, all of a sudden I was like, they didn't give that to us, but they gave us A. And so then the probability of not A is going to be 1 minus that. So this right here is 1/4 would be equal to the probability of B intersect A naught divided by 3/5. Since I have some number that's being divided by a fraction, or it doesn't matter what it's being divided by. I have something being divided. How do I undo division? I multiply. So I'm going to multiply both sides by 3/5. And I get 3/20. So the probability of B intersect A naught is equal to 3/5. So that means B intersect A naught is this right here. It's 3/5. So this probability of B, this becomes 9/15. 9/15 plus 2/15 is the probability of B would equal 11/15, which you will notice is not the probability of B given A over here. Okay, so are they independent? No, not independent. Okay, I'm too lazy to write out the word. All right, okay, that one was a little hairy. If I have any probability experts, comment below and see if you agreed with my explanation. Okay, find the probability of A union B given A and B. Well, we know they're independent events, so, well, we always know this to be true. That's always true no matter what's happening. But if we have independent events, then we know that the probability of A intersect B is equal to, hang on, it's equal to the probability of A times the probability of B. Okay, so let's plug in what we know. A is 0.3, the probability of A. The probability of B is 0.4 minus 0.3 times 0.4. I have 0.7 minus 0.12, which is equal to 0.56, not 6, 58. 0.58 if you feel like being so particular. And the last one we did was find probability of B if they're independent. Well, we just said probability of A union B is going to be equal to the probability of A plus the probability of B minus the probability of the intersection. But because they're independent, that's equal to this. I just didn't feel like writing it twice. There you go. What can I plug in? This is 11 over 20. This is 2/5. We don't know the probability of B. Oh, haha, I messed up. Did you see it? I forgot that plus sign. Okay, and then this becomes, I need to multiply them, but not right there, I don't. Okay, so it's 2/5 plus the probability of B minus 2/5 times the probability of B. So the probability of B minus 2/5 of the probability of B is equal to 3/5 of the probability of B. But I still have this 2/5 here, and it's still equal to 11 over 20. Subtract this away. This is what, 8 over 20? So this gives me 3 over 20 is equal to 3/5 times the probability of B. Let's multiply both sides by 5/3. And I get 1/4 is equal to the probability of B. That was fun. All right, like, subscribe, comment, and as all things, you have to go practice if you want to learn math. Good luck.